This is really the recent results I will show are really the work of some bright young students and postdocs that were in my group recently. So Matteo Crispino, Maria Cassia Lefteriu, Paolo Villar Arribi, and Tommaso Gorni, but also some long-standing collaborators with Giorgio San Giovanni in Würzburg, Massimo Capone in Trieste and their groups, and collaboration with the experimentalists of the group of Christoph Meingast in Karlsruhe. Then I will also quote some older results from long-standing collaborators, but these are for the more recent results I show. So I will be discussing the modeling of strongly correlated materials through multi-orbital Hubbard models. We know that when we do this when band theory doesn't describe well a solid, and we introduce the effect of local interaction explicitly and the local correlations that this generate. Typically, we do this by using a tight binding model into which we plug the effect of the explicit effect of Coulomb interaction, in which we differentiate the repulsion that the electrons feel when they are on the same orbital on a site, or when the reduced repulsion when they are on different orbitals, depending also on their spin orientations. Here I put the simplest Hamiltonian way which does that, and in general I will be talking about either models or realistic materials. The difference being that in realistic materials, this one body part of the Hamiltonian will come from a fit of DFT band structures. In models, I will only have bands with diagonal hopping, so this hopping will be just a delta function in in orbital space. Now, this Hamiltonian, of course, has other possible terms, but in the results I will show, these terms play no qualitative role. So in the Hund's coupling J, which is the measure of how differentiated is this interaction locally, is typically a fraction of the Coulomb interaction from 0.1 to 0.23. It really embodies the fact that what matters are how favored are local atomic configurations in the expansion of the wave function, which is really a many-body wave function. So we know that using Slater determinants is not enough, and so we have to deal with the explicit group pictures of the electrons on an atom. So DMFT and Slade spin-mean field, which is another embedding method, which is equivalent to Gutzwiller approximation or Slade bosons, really bring this point of view of what does the atom do in the creation of the metallic state. So in particular, this Hamiltonian brings in the fact that high spin configurations of electrons that go on that distribute on all possible orbitals are favored among these local configurations, and this is exactly what we know from chemistry, from atomic physics as the Hund rules. Now, one way I like to illustrate the importance of this aspect is the following. So imagine that you have independent bands, a set of independent identical bands. So they don't talk to each other, neither they don't have hopping, and we have only intra-orbital interactions. So these are isolated bands, and they do what we know they do when you increase the Coulomb correlation. The quasi-particle weight diminishes as a function of U, and then at some point vanishes, bringing so creating what's known as a Mott insulator. Now you can be tempted to portray this as the competition between the kinetic energy of the band electrons and the repulsion of the electrons when they found on the same site. However, imagine if you do this. Imagine you take this collection of bands and you turn on further repulsion, which is the repulsion between the bands. So the interorbital repulsion, both for parallel and non-parallel spin. You have added repulsion, and what you get is in a contradictory way to what you might expect when you think about the competition between kinetic energy and repulsion. You get a less correlated metal, and actually a Mott transition which happens for further for a stronger repulsion. Now imagine you do the following. You reduce partially this repulsion, which is what you do when you turn on Hund's coupling. So the interorbital repulsion is made smaller. And you might imagine that you reduce the effect of Coulomb interaction, and you get exactly the opposite. So you get that the Mott transition happens much earlier and even earlier than the single band case. So if you were tempted to describe it as a competition, just simply intuitively as a competition between repulsion and kinetic energy, this might maybe hold here at very weak coupling, but certainly not a strong coupling, where what matters is actually these local configurations and how the many-body wave function fluctuates between these local configurations, which are ultimately regulated by the degeneracy of the ground state and how this combined, how many states can be combined into a many-body state, and the many-body kinetic energy that this has, depending on the available and active hopping channels. And this ultimately regulates the critical U. So there are two main effects that the Hund coupling has. One is to split the ground state multiplet, so reducing the degeneracy, and so basically creating a many-body superposition of states which has a harder time hopping around, so basically increasing the correlation of the system. On the other hand, there is a simpler effect which is already obvious in the atomic limit, which is the way it tunes the energy of the different charge sectors. And what we see here is for each charge sector of different color, the range of chemical potential where it is a ground state. And what you can see for a sizable Hund coupling typically used in our calculations is that there is a zone of chemical potential which is pretty small, in which a lot of different charge sector change, the ground state changes quickly among different charge sectors, and a lot of them have comparable energies. And this happens both for less or equal to half filling, which in this model is 5, because I'm looking at 5 orbitals, a 5-orbital Haber model, and for more than half filling and half filling. So these are two restricted zones in chemical potential. And then you can see that there is a large zone of chemical potential around particle symmetry, which is completely dominated by the half-fill sector. So what this means is that Hund's coupling puts charge sectors close in energy when you're when you have electrons more than half or less than half, and at particle symmetry, it rather pushes all the sectors away in energy, and so it increases the gap to charge excitation, but only for half filling. For out of half filling, it actually reduces it. So these two effects I mentioned can be combined, and this was some early study we did with Antoine and Yerne. And we saw in a typical situation of 3 orbitals that the two effects collaborate at half filling, 3 electrons in 3 orbitals. So they reduce they correlate the system overall and make that the system is very prone to a Mott transition. And on the interesting case of 2 electrons in 3 orbitals, they actually fight each other. So the Mott transition is pushed away, because the charge excitations get closer in energy, but the system gets overall correlated, giving rise to this typical plateau that we now learn to associate to Hund's physics. So these two fighting effects, we call them with a nickname of the Janus Roman god, which had 2 faces looking in opposite directions. So now there is a very nice review from Antoine and Gabi that just came out on Physics Today, which finally defines the Hund metal, both with this typical plateau, where you have low coherence and strong correlations for a quite extended range of interactions, and by the fact that the multiplets are the different charge multiplets are visited, so there are a lot of charge fluctuations, but in each multiplet the high spin state dominates. Now here I would like to quote that some of these concepts were already around in the past, and that a coherent image is emerging now. But this came out about when people were trying to understand why some on the basis of the bare energy scales, some materials were expected to be both insulators and were metals, or vice versa. So now another recent historical point is that in iron-based superconductors, in the research of iron-based superconductors, the actual Hund metal word came about. And this is because these are very quintessentially multi-orbital correlated materials. So all happens in a buckled plane of iron and ligands in the different families. And this plane has a partially lifted degeneracy, but all 5 orbitals are participating to the conduction bands, are of 3D origin of iron, and they host 6 electrons in 5 conduction bands. So this thing is not half-filled, but is the next integer filling. Now, when doing calculations very early on, the group of Gabi Godler and Christian Haule, they realized how much realistic calculations for these materials were sensitive to the explicit value of the Hund's coupling that they chose, and how much Hund's coupling was really triggering very early in temperature departures from Fermi liquid physics. So was lowering the coherence and actually enhancing the correlations in these materials. And it was in a subsequent paper that they coined the word with Ziping Yin, Hund metals. Now, what I would like to point out today is the role of mode physics in this respect. So you can put 2 electrons, as I showed, in 3 orbitals and see that the fact that they have to align, the tendency that when they have to align, generate this typical plateau and low coherence scale and low Z. But now you can put 2 electrons, or here 2 holes, when I write 8 n equal 8, in 5 orbitals, okay? And you see that this effect is much less pronounced. So still they have to align when they hop around, but clearly the situation as far as the local multiplets is slightly different. And what you see strikingly is that when you go towards half filling, so 7, 6, towards 5, which is half filling, the effect of the Hund's typical signature of the Hund's metal, so this plateau, becomes more and more pronounced. So I'd like to explore the fact that when you go toward the half-filled Mott insulator, because at TCU you have a Mott insulator for half-filling, the Hund's physics becomes extremized. And this was already clear from some calculations here I published a few years ago, in which here you see all the possible fillings, I mean the central ones from 0 to 10 that you can put in a 5 orbital Haber model. As the color code is the quasi-particle weight, so a light color means a very strongly correlated metal. And here, as a function of the interaction strength for some ratio of the Hund's coupling, these black bars are the Mott transitions that can happen at every integer filling. And here in the square, I locate more or less where you put in such a model the iron-based superconductors. Now, if you increase Hund's coupling, see what happens. So the Mott transitions go away to very, very high U. And basically, the quasi-particle weight seems very much regulated by the proximity to this Mott insulator at half filling, which instead was pushed down, so it was favored by Hund's coupling. Now, this was already observed in some model studies or has been characterized with other techniques. So here was a very early paper from Werner, Gould, Troyer, and Millis, where they really showed that in the 3-orbital Haber model, while approaching half filling, which is now here 3, you go from a weakly correlated Fermi liquid to a very strongly correlated zone, which at finite temperature appears as a frozen moment zone. And they could even, I mean, the transition is so sharp that they could even trace a frontier, which lately was seen to rather be a crossover, at least part of it, into a strongly correlated zone, which is extremized then by approaching half filling. And another characteristic which has been used to characterize the Hund's physics, which is the spin orbital separation, here studied by the group of von Delft together with Gabi Kotliar. You can define a low coherence temperature for the metal, which coincides with the Kondo temperature for the spinning of this local moment that we saw in the frozen moment. But there is another temperature which characterizes the freezing of the orbital fluctuations, which is much, much higher in temperature. This incidentally gives rise to striking evidence on strontium, ruthenium 04 and other ruthenies, which are another typical example of Hund's metal, which is extremely studied in this period, in particular by Antoine and his collaborators, but there are many other papers appearing. And this Seebeck data can be interpreted if you take into account that only the spin the fluctuating spin contribute to the entropy. So this hallmark of Hund's physics also is seen to be extremized when you go towards the half-filling, which here again is 3. So, and by the way, if in these systems you do explicit calculations, for instance, in absence and in presence of Hund's coupling, you really see an immediate drop of the Hund's coupling for the whole range of interaction strength, in which you can flank the Mott insulator. And typically, the linear dependence of the Z as function of doping is also seen to be much, much lower when you have Hund's coupling than when you don't have it. And even compared to the single band case, which goes together with the very first evidence I showed you, in which the U critical was lower than the U critical for a single band Mott insulator. All these come from the same physics, from the same matrix elements, and really shows that Hund's coupling favored this strong correlation. By the way, this was also evident in the calculations that we did for the iron-based superconductors. Here, typically, is the 1 to 2 family, which can be whole doped from the 6 electrons in 5 orbitals all the way toward 5.5 electrons. So approaching the half filling at 5 electrons. And here in blue are the experimental points of the Sommerfeld coefficient from the specific heat, which really is enhanced when strong correlations increase. And you see these green points are the theory, which reproduces the experiments only when you have a correct value for the Hund's coupling. If you take it out, you basically fall back on the results here in black from DFT, so from band theory, which are completely off. So this really shows how approaching the Mott insulator that you would get half filling, you have an increase of physics, which is entirely due to the presence of Hund's coupling. So we studied this transition at half filling and the neighboring filling, so the doped Mott insulator at half filling. One thing which was known in the literature is that as soon as you turn on Hund's coupling, the transition becomes first order, as is illustrated here in the 2 orbital case, but it's true for all other cases. And this was, again, known in the literature from different techniques. So we wanted to really clarify this issue. And what we did, we studied with DMFT and numerical renormalization group at 0 temperature. So we realized that this transition that, again, here is illustrated by the fact that Z drops from a metallic solution in blue to an insulating solution in red, which then goes on for a higher interaction strength. This goes from through a jump, a discontinuity, which is actually here portrayed by the difference in the 2 spectral functions of these 2 solutions. And that what we found is that this jump happened and was characterized by the fact that the 2 solutions are actually adiabatically connected through a 3rd branch, which is unstable and metallic. Then we decided to study what happens once you dope in this zone of coexistence. And when you move the chemical potential, indeed, what happens is that the metallic solution is immediately doped. As you see here, when you move chemical potential, you get doping. Whereas the insulating solution coexisting has a plateau, and it's eventually doped. And still we see that there is an adiabatic connection between these 2 solutions, which is then metallic and also immediately doped as soon as the chemical potential is non-zero. And that once you increase the interaction and you go beyond a larger value than the U for the coexistence zone, this sigmoidal shape actually unfolds more and more until for some larger U, the dependence of doping on the chemical potential becomes monotonic again, and then you recover a normal metallic solution for the whole range. So there is an instability, which is basically characterized by the fact that then you have diverging compressibility at these two spinodal points, which delimit the unstable branch. And so you have divergent compressibility, which is the derivative of the density as a function of the chemical potential, which then resists also beyond the closure of this zone. So we can basically trace a phase diagram using these spinodal points and put them in a U versus doping plane. So here at half filling, you have the coexistence zone signaled by this dashed line and the Mott insulator for larger interactions. And you have these spinodals crossing here and ending in a quantum critical point, which is exactly the point where the unstable solution vanishes and the solution becomes monotonic again. And then you see that across this zone, you have a transition between a weakly correlated metal, which is this branch, and a much more strongly correlated metal. I didn't show it here, but the Z quasi-particle weight is much lower for this branch. So that in the end, when you take into account that you have to, that thermodynamically, one has to make a Maxwell construction here, and then basically that this implies phase separation or in general charge instability between a metal and an insulator, or between the two metals around the solution. The final, a universal phase diagram becomes the following one. So first order transition between a weakly correlated metal and a strongly correlated metal, which is dominated by the fact that it's actually the proper doped Mott insulator. So that's what I tend to identify with the also with the zone where the strong correlation due to Hund's physics starts to happen, so the Hund's metal. And then the phase separation ends in a quantum critical point where the compressibility diverges. And beyond this, one still has a signature, which is a signature of a peak in compressibility, which can actually be detected even in the stable zone. So I tend to identify this frontier with, for instance, at finite temperature, the spin freezing frontier, which at zero temperature now gives rise to a continuous transition for some range, a discontinuous transition in other range, and a quantum critical point where fluctuations of density diverge at some finite doping, which is not negligible at least 10% doping in the two orbital case. I won't enter much into this, but just to tell you that this can be completely analyzed and through a Landau theory, and the double well structure typical of a first order transition can be seen due to the splitting of the ground state multiplet the small splitting due to Hund's coupling. So it's really triggered by J, and so this triggers the first order Mott transition, and all this folding of the equation of state and the unfolding that happens for increasing doping that ultimately gives rise to the quantum critical point. So then we analyze this in more than two orbitals, only to see that larger number of orbitals increases the range of doping where this instability happens. Here I'm just raising the spinodal, so it appears small, but one has to do the Maxwell construction around all this. And that crystal field splitting enlarges even more the range, so much that, and also the density-density interaction, it's actually more prone to a large zone than the fully rotational invariant Kanamori interaction. This is the detail. But in general, the lower symmetry helps extending this instability zone, so much that if for 5 orbitals we realistically splitting for the iron-based superconductors, this zone extends all the way from 5 electrons in 5 orbitals, so half filling where it stems from, to all the way to 6 electrons in 5 orbitals, which is where the stoichiometric iron-based superconductors are found. So much that then we decided to apply to all realistic calculation of iron-based superconductors, which are all here. This is more the work of Pablo and Tommaso. I will summarize this very quickly by saying that we find this moustache, so either the charge instability or at least the enhancement of compressibility which stems from it, always where we find the highest TC. It seems to correlate with the TC in the different compounds. And there are several ways to correlate charge instability and the frustration of a phase separation, as we know from cuprates, to the insurgent of ITC, or at least helping the ITC, as it might be the case for iron selenium or the monolayer of it, in which the boost can happen either directly through this the critical density fluctuations, or through the increase of electron phonon coupling, which seems to be playing a role in iron selenium. In my last 5 minutes, so Olivier, I think that's my cue. I'm giving it
exactly.
Okay,
exactly
great.
5 minutes.
I would like to show another aspect of Hund's physics, which we explored recently, and the fact that it came clear by studying models already that in proximity, so when the Hund's coupling favors the orbital differentiation of correlation strengths. So meaning that electrons, depending on their orbital character in the conduction bands, they can show different degrees of mass enhancement or a quasi-particle, inverse quasi-particle weight. And this was even found quite strikingly in a work that we published with Gianluca Giovannetti and Massimo Capone, in the same family I showed you before of the iron-based superconductors, the 1 to 2 family, that can be doped from 6 electrons in 5 bands to 5.5. And the spread of these different estimates, I will not enter into this, but the increasing spread of these estimates of the mass enhancement can be interpreted as increasing orbital selectivity of the correlations. In particular, the XY orbital, which is the closest to half filling, is the one that shows most correlation strength and dominates the highest estimates. Now, this is perfectly captured by theory, obviously in presence of the same value of the Hund's coupling that we said before. And so one possibility is to ask oneself, okay, can one extremize also this behavior, and which starts resembling to a heavy fermion behavior, because some electrons are consistently and strikingly heavier than other electrons. So this is what we suggested and what we actually did with our colleagues in Karlsruhe. We asked them to take the most correlated of the whole doped iron-based superconductors, cesium, iron 2, arsenic 2, and to try to further whole dope it. The way this can be done is by substituting chromium to iron, which is already a substitution being practiced in the same families, and it has the good taste of not altering any other parameter besides some disorder, obviously, then doping hole in the plane. So the lattice parameters are kept constant. So our experimentalist friends actually made it into putting a few % of chromium in this cesium iron 2 arsenic 2, and indeed they were able to find a record Sommerfeld coefficient of 270 millijoule per mole Kelvin square for 3% chromium. And this starts being in the ballpark of the F electron heavy fermions, with the advantage, the possibility of exploring d electron heavy fermion physics to not having to deal with F electron materials, which can be sometimes rare or radioactive or complicated or hard to get or to extract and manipulate. So this seemed to us a good idea to give a systematic method to find new electron-heavy fermions, new heavy fermions based on the electrons. Indeed, these are their data. So one sees the specific heat divided by temperature, or the extrapolation is actually this Sommerfeld coefficient going up between the early dopings. This still is characterized by resistivity, which has a Fermi liquid form, and thermal expansion, which is a normal thermal expansion coefficient that we have here for a Fermi liquid. Then something interesting happened for extreme chromium content, which is this point over here. So the Sommerfeld coefficient changes completely, the behavior changes completely. The compound becomes non-metallic, and even the thermal expansion inverts its sign, which basically tells that instead of increasing correlation with negative pressure, they increase with positive pressure. So this can be interpreted in terms of entering an antiferromagnetic zone, which is predicted by our calculations. I won't really enter into the details. This is the result of the work of Matteo Crispino. But in general, we think that this goes even more into the general idea of exploring heavy fermionic physics with this Hund's physics. Because if you take a Hund's metal, which is orbitally differentiated, and you go towards half filling, and you dope it towards half filling, so you extremize both the Hund's physics and the orbital differentiation, and still the heaviest electrons are in principle they don't have the real possibility of doing an orbital selective mode transition because you have hoppings between the different orbitals, or at least local correlations cannot, and this can be shown analytically, give us an orbital selective mode transition. So basically you obtain this long plateau without fine-tuning of extremely low coherence, exactly as you find in a F electron heavy fermion. Then, as we saw, and we know in F electron heavy fermions, a magnetic phase can kick in. In F electrons, it's typically due to RKKY interactions. In D electrons, it's more super exchange. And this can give rise to two typical scenarios that are studied in what is called the Doniak phase diagram of heavy fermions. One in which you have just a cut of the Fermi liquid from the magnetic phase, another in which you actually have a vanishing scale of the Fermi liquid in the exact point where the magnetic phase happens. And this can be due from the unavoidable no-local correlations that can actually, this can be shown, drive the system into an OSMT, because there the mass can, I mean, the quasi particle weight can go to zero without the mass diverging, which is what the local, the interorbital hopping actually frustrates. So I go to my conclusions. I hope I have convinced you that whole material physics is nice, is very interesting, and most of all, that is extremized when approaching the half-filled Mott insulator, so much that in the surrounding of this half-filled Mott insulator, thanks to the Hund's coupling, we have both a frontier that basically divides a weakly correlated metal from an extremely strongly correlated metal, which is the proper dope Mott insulator, which I would like to identify with the Hund's metal phase, and which extends all the way to very, very large doping. This frontier actually has an instability to phase separation or charge instability in general that finishes in a quantum critical point. And by approaching this Mott insulator in a system which has actually broken the orbital symmetry, the orbital selectivity of the correlation cell can actually be extremized, and a physics of the kind of Doniak phase diagram, and in general a systematic way to explore and find new heavy fermions based on d electrons, it can be foreseen. Thank you very much for your attention.
Thank you very much, Luca. So we will now take questions. So if you have a question, you can raise your hand and we will allow you to unmute. You can also write it in the Q&A. So Karsten.
Hi, Luca. Very nice talk.
Thank you.
I have a question regarding this orbital selective Hund's metal. So for the Hund's metal, you have a separation of the orbital and the spin condo. And now, of course, this orbital condo can be first in some orbitals and then in others. But if you go to zero temperature, you have all condo effects, or are there really phases where you only have the orbital condo for some of the orbitals, but not the others, or only orbital, but not spin condo effect?
Okay, that's a very interesting question. I don't think I have an answer, because all these are temperature effect, and some of them happen at very high temperature. So I mainly really focused on.
So your definition is with respect to temperature, that you get different temperatures for different orbitals and for
Exactly, or you can explore them as a function of energy too. But I think in order to actually have this answer, one has to really do extend the energy studies to realistic cases, which is still a frontier. Now, I remember that in the end, as far as the Fermi liquid scale is concerned, is when you get everything screened. So this would coincide with the lowest screening spin.
Yeah, therefore, also my question is whether you can really get rid of one of these screenings and still the others being metallic.
I don't see why not, but yeah. So this would be what is basically observed in as temperature-induced orbital selective mode transitions, which are now, for instance, observed in iron, selenium, tellurium. So certainly you can cross in temperature just one of these scales, because
that's clear. Okay, thank you.
Antoine?
Yeah, perhaps just in connection with Karsten's question. So really stabilizing this down to zero temperature, I mean, what Karsten has in mind would require some quite special zero hybridization case, no? Because if you start having hybridization between orbitals, don't you think it's always going to be essentially relevant in the zero temperature limit?
Yeah, absolutely.
Yeah, the Hund's exchange could split it, huh?
Yeah, I don't think if there is really an OSMT regime stable down to T equals 0. I don't know what you think, Luca.
No, I think with local correlations, this, I think it can be shown to be impossible. Yeah, at least unless special cases, of course, are concerned. But it seems to me that you can show that basically the kinetic energy of the electrons. So if you are in a Fermi liquid formulation, you can always write the kinetic energy of the quasi-particles as a band with normalizations. If you were to send only one quasi-particle mass enhancement to 0, that would give you a logarithmic slope in the dependence of the kinetic energy on Z. So basically, you can never have a minimum of the energy for a Z equal to 0. Now, if you have no local correlations in which you can send, in which Z, in the sense of the quasi-particle weight and the mass enhancement, are disconnected, then you can send one Z to 0 without incurring into this singularity in the kinetic energy of the band structure. In that case, so with no local correlations, you can stabilize an OSMT at 0 temperature. This was actually studied by Jan van Delft recently with NRG.
Thanks.
Are there any other questions?
Ugo.
Ugo has a question.
So naive question. So the phase separation that you find, so I think this, what you're showing is for J over U 0.25 or something?
Well, it's for all J's, but yeah,
Okay.
what we show here is this explicitly, this phase diagram is for 0.25.
But we know that something magically happens as we push this above 1/3, right? So then we get phase separation already in the atomic ensemble.
Absolutely.
So how does this evolve as we crank up J over U? How does this picture change?
Well, I think there is a real difference in regimes once you cross the 1/3 plateau when J is U over 3, because simply you have local attraction on each side. But here I think of course the fact that U minus 3J is small, these plays are all here exactly because we have this as I showed in the beginning, the different charge sectors actually do compete, and so charge fluctuations tend to diverge exactly because all these charge sectors are degenerate in energy. So the perfect degeneracy happens at U the J equal U over 3. So in that case, even the atomic model would have like a whole infinite compressibility, if you want to say so. In an atomic model, it doesn't really make sense, but from half filling to all the possible charge sectors together. So then after that point, J equal U over 3, then the physics changes completely, as you have studied quite early on.
Okay, thank you.
Antoine, you had a comment?
Yeah, maybe it's better if Sung Soup
Yes.
speaks because I've already spoken. So
Yeah.
Thank you for the next stop. I have a question regarding this upper left figure. So you had say 4 points for the unstable branch for this 2-orbital model.
Yes.
And how does the spectral function look like for those 4 points?
Good question. We didn't really look too much into it. I mean, I do have the data, yes, but because this being unstable is basically, I mean, we didn't characterize it physically so much, but if I remember well, it looks a little bit like this metallic branch. So with a peak in the middle, which is diminishing in width, but well, I don't want to tell you anything more detailed than that because I frankly do not remember more details.
All right, good. Yeah, thanks.
But again, I mean, we can discuss separately. I can dig out my data.
Sure. Actually, we are also trying to reproduce the data.
Yeah, well, it's very hard to stabilize, to have convergence in this unstable point. So there are some tricks to be needed, but a point is considered converged when you actually have very little. I mean, when you're self-consistent to under some error bar.
Yeah, sure. Thanks.
Okay, I think we should